Hey everyone! So this video is all confidence interval practice problems. So this video is going to focus on confidence interval construction when we're using a normal distribution. We use a normal distribution with confidence intervals when we know the population standard deviation, right? Okay, so no t-distributions, no t-scores in this video. We're going to focus on z-scores and the normal distribution. Let's get started. So let's review step by step how we deal with confidence interval problems. And remember, this is for when we actually know our population standard deviation. So first you want to figure out your x bar, your standard deviation, and your sample size from the problem. Then you want to calculate the standard error of the mean, and you use this formula every time that you're using z-scores and you have a known population standard deviation. Take that known population as the, and you're going to divide it by the square root of the sample size each and every time. Your third step is to figure out what alpha is, and then also to recognize what alpha divided by 2 is and how that's distributed in your distribution. You're going to use the Bogner applet to find out what the appropriate z-score would be related to that confidence interval. And here's that short link for your computer or phone. And remember, when you get to the app, you're going to enter the entire alpha, not alpha divided by 2, into that space. And we'll review how to do that when going over our practice problems. And make sure you select this parameter that evenly distributes your alpha between the tails. Once you have your z-score, then you're going to calculate the confidence interval using all the components that you know. So you calculate your error-bound formula, what we call our EBM, and that's when we know our population mean and our population standard deviation. So we take our z-score that you've calculated using step 3, and you're going to multiply it by the standard error of the mean that you calculated in step 2. That will give you your error bound. And finally, your confidence interval is constructed as follows. Take that x bar and subtract the EBM calculated above, and then x bar plus your EBM calculated above. And finally, we just write out a complete sentence that explains the confidence interval to a layperson. When we're using the Bogner app, we have to indicate our alpha, our full alpha for the app. But visually, what we're saying is we want the bulk of our confidence interval to occur here in the center of our normal distribution, symmetrical about the mean point. And then we have alpha divided by 2 in one tail and alpha divided by 2 in another tail. And what we're doing is we're saying starting from the mean, we're going to subtract one error bound, and that will be 1 point on the outside of our confidence interval. And then we're going to add that same amount, that same error bound, to our x bar, and that's going to form the upper bound of our confidence interval. And so this area under the curve corresponds with the probability of your confidence interval, right? So just as a reminder, let's say we were doing a 98% confidence interval. What would our alpha be if we had a 98% confidence interval? Our alpha, if we set our confidence interval to 98% or 0.98 as a proportion, 1 minus our confidence level would be alpha, 0.02 or 2%. We would distribute that amount between the two tails. So 1% of the area under the curve would occur over here to the right of our confidence interval, and 1% of the area under the curve would occur over here to the left of our confidence interval. Our written interpretation should clearly state the confidence level, explain what population parameter is being estimated, and state the confidence interval, both endpoints, and the units very clearly. So here we would say, we estimate with 98% confidence that the true population mean of, and we would include the context or the variables and units of our problem, is between, and we would say our lower bound and upper bound, and we would include units like days or inches or whatever other measurement we were using for our problem. So let's look at a complex problem, and it includes a lot of practice in comparing between two confidence levels. So, a sample of 16 small bags of the same brand of candies was selected. Assume that the population distribution of the weights of bags is normal, okay? The weight of each bag was then recorded. The mean weight was 2 ounces with a standard deviation of 0.12 ounces. Okay, here's an important clue about solving this problem. We know the population standard deviation. So that's going to indicate to us that we should use a normal distribution. Let's go back to the problem again. It told us the mean weight was 2 ounces of this sample of 16 bags of candies, right? And it gave us a standard deviation of that sample of 0.12 ounces, but that's a really small sample. We want to feel confident going forward, so we're going to use the known population standard deviation and use our normal distribution to solve this problem. All right, so step one in solving this problem is figuring out and identifying all of the important information that we need. We know that our mean weight was 2 ounces, so that's our x bar. What is our known population standard deviation? Exactly, 0.1 ounces. And we were also given the standard deviation of that single sample. Let's write that down too. That was 0.12 ounces. Okay, in words, let's define the random variable x. When we talk about the random variable x, that's talking about the original distribution. So what was that? The weight of candies. In words, let's define the random variable capital X bar. Capital X bar is the sampling distribution of mean weights of our candy bags. See the difference? Part D asks us, which distribution should we use for this problem? Explain our choice. Well, it's asking us whether we should use the normal distribution or the t distribution. Now, since we have a known population standard deviation, we want to use z-scores for our error-bound calculation, so we're going to use the normal distribution. Now we're asked to construct a 90% confidence interval for the population mean weight of the candies. So I'm going to do that math on the next page, but I wanted to remind you how you can find the z-score using the Bognar app. So if I wanted to find the z-score associated with a 90% confidence interval, I'll open that Bognar app that we've been talking about. And what you want to do is set your mu, your population mean, to 0 and your standard deviation to 1, because that sets up a standard normal distribution. This is our way that we can use the app to tell us the z-score instead of having to use a clunky z-table, right? So here is where we're going to enter our full alpha into this red box, and we want to make sure that we've selected this particular parameter, the one that starts with 2p, because that's telling the app to put all of that probability of alpha evenly distributed between the two tails of our distribution. So make sure that you've selected this parameter and then enter the full alpha here. In this case, our confidence interval was 90%, so that means our alpha is 10%. What that means is that 5% of the area under the curve will be distributed here, alpha divided by 2, to the left of our confidence interval, and then alpha divided by 2, 5% more of the area will be under the curve to the right of our confidence interval. Here in the center will be that 90% of the area under the curve that will make our confidence interval symmetrical about our mean. So when we enter this information and we click away, what we get is x equals about 1.64. And that's the z-score that's associated with a 90% confidence level. So this is great. We'll use that information on the next page for our calculations. So again, as a reminder, because we knew the population standard deviation, we're going to want to use z-scores for this problem. And we also know that when x bar is normally distributed, that sampling distribution of the means is normally distributed with a mean that approximates the mean of the original distribution, and standard error of the mean is the standard deviation of that curve. So we use this to help us calculate our error bounds. When the population standard deviation is known, as it is in this problem, we want to use that normal distribution to calculate the error bound. The error bound formula for a population mean when a population standard deviation is known is the z-score that corresponds with your alpha level, and then the standard error of the mean. So we knew that for a 90% confidence level, that we were going to need to use the z-score 1.64. Now we want to multiply our z-score by the standard error of the mean. We were given that the population standard deviation was 0.1, and we were given a sample size of 16, so we're going to take the square root of that for our denominator. Let's simplify that. Now we can use this error bound to construct our confidence interval. We know that our mean value is 2, and that we were going out about 1.64 standard deviations above and below the mean. This area in the center is our 90% confidence interval, because this is 90% of the area under the curve symmetrical about the mean here in the center. Here we have alpha divided by 2, which is about 5%, and this is alpha divided by 2, which is also 5%. Now that we've calculated our error bound, we can label the points that serve as our lower and upper bounds of this confidence interval. 2 minus 0.04 is about 1.96, and 2 plus 0.04 is 2.04. Before we write out our interpretation formally, take one more look at this graph. Do you understand what's happening? We have 90% of our area under the curve, here in the center, symmetrical about our given mean, which was 2. And we're saying that we are 90% confident that the true population mean of the weights of candy bags lies somewhere between 1.96 ounces and 2.04 ounces. Instead of just giving a point estimate and saying that it's about 2 ounces, we actually have an interval that serves as an interval estimate. We know with 90% confidence that the true population mean of our candy weights is between 1.96 ounces and 2.04 ounces. Let's write out our interpretation given this formula. We estimate with 90% confidence that the true population mean of the weight of candy bags is between 1.96 and 2.04 ounces. Yes, don't forget the units. The problem now continues by asking us to calculate an even larger confidence interval. Instead of a 90% confidence interval, now we're challenged to calculate a 98% confidence interval. So we're going to do the same work of constructing this confidence interval using a different confidence level. And then after, we're going to need to compare why these two confidence intervals are different and have different values. Then we're going to interpret what this new interval means. When I need to know the z-score to calculate my error bound, I'm going to use the Bogner app. And again, we want to set this up so that it serves as our standard normal distribution. So I set mu to 0, and I set my standard deviation to 1. It's just by the definition of the standard normal distribution. And then I want to enter my full alpha here, making sure that I've selected this option that evenly distributes our alpha between the tails of our normal distribution. In this case, when we have a 98% confidence interval or a 0.98 confidence interval, if I'm writing it as a proportion, here I write my alpha as a proportion 100 minus 98 is 2, or 1 minus 0.98 is 0.02, so I enter that 0.02 here. That's my alpha. And then when I click away, the app is going to evenly distribute alpha divided by 2 between the two tails, and it's going to have this 98% confidence interval here in the center of the graph, symmetrical about 1. And the given value shows up here in this blue box. 2.32 is our z-score. So we're going to use 2.3, let's round to 2.33 for the purposes of our problem. Again, we know our population standard deviation, so we're going to use the normal distribution and z-scores to answer this problem. Again, we have the same error bound formula as before. We're going to take our z-score and multiply it by the standard error of the mean. So let's set up our calculation. All right, now that we've calculated our error bound, we can sketch the graph and calculate our confidence interval. So this time, we know that our z-score is 2.33, so that means we're going to go about 2 1/3 standard deviations away, above and below the mean. All right, so that's about here and about here. And we're saying that 98% of the area under the curve occurs here, in the center of the graph, between these two endpoints. That means about 1% of the area under the curve occurs here to the left of this lower bound, and 1% of the area under the curve occurs here to the right of this upper bound, right? And just as a quick reminder, that's because we know the total area under the curve always equals 1 or 100%. So 1% plus 98% plus 1% equals 100%. We're good to go. So now let's label these points. We were told that the mean that we were given, our x bar, was 2. So that's our center point, 2 ounces. So if we subtract 0.06 from 2, that means that our lower bound here is going to be 1.94 ounces. Awesome. And then we add 0.06. So we are 98% confident that the true population means of these weights of these silly bags of candies lies between 1.94 ounces and 2.06 ounces. Now, do you remember what our confidence interval was before? Let me write these confidence intervals side by side so you can compare them. If I wanted to be 90% sure, my confidence interval that we calculated was between 1.96 and 2.04 ounces, right? However, if I wanted to be 98% sure, my confidence interval was going to be between 1.94 and 2.06 ounces. That's 0.04 ounces larger than the confidence interval for 90% confidence. So this is kind of a lesson to put in your back. If you want to be more sure, more certain of your confidence interval, if you raise that proportion of confidence, by definition, you are going to have to increase your confidence interval. So your bounds, your lower bounds will be even lower, and your upper bounds will be even higher. So you need to increase the width of that confidence interval if you want to be increasingly confident. So let's write out our written interpretation for practice. We estimate with 98% confidence that the true population mean of the weight of candy bags is between 1.94 and 2.06 ounces. As always, I have my top 3 takeaways from you that they're not comprehensive, but just to make sure we're all on the same page. 1, I want you to keep making sense of this visual. Your confidence level is this shaded area symmetrical about the mean here in the center of the normal distribution. And then we have alpha divided by 2 here in this left tail and in this right tail. And this is how we set up our confidence interval every single time. This is our formula. Of course, you can always use course materials on exams, but it's good to memorize this formula. If you have the population standard deviation, if you know that information, here's how you calculate. You take your z-score associated with the alpha that you're given, and you multiply it by the standard error of the mean. So just keep practicing with these confidence interval problems. All right, everybody, thanks so much, and I'll see you in the next video.